essentially, imagine you have like 4 macros, right? Or just like an intersection, right? Where everything come in and then connect to 4 sides, right? So top, bottom, left, and right. So essentially you have one vertical channel and one horizontal channel, right? When they intersect, let's create the switch box, right? So okay. So yeah, I think we all know the net is, but this is just the official, the formal definition of it. It's just a set of 2 or more pin that's have the same electrical potential, right? So, but we very much know what a net is. It just connect to all of these pins, right? 2 or more, right? So, and the netless is just a collection of all those net of the design, right? So, um, yeah, one of the uh, terminology that's very important during routing is congestion, right? Talking about, it mentioned about if things didn't go right, then one of the things that we look at is the congestion, right? That's the indicator of something is not quite right, right? Something go wrong, you're gonna see it right here. So the congestion, right? Because ultimately, if you have more wire than the resource, right? The routing resource, then you're not going to be able to route the chip, right? That's simple as that. No, not overall, but locally, if there's an area of the chip that you can't, you simply can't force more wire to an area that has no routing resource. It's not going to work, right? So and the congestion is we're going to spend time on a look at different metrics, how to kind of like understand the report, congestion map, and figure out what's wrong, right? Yeah, a couple of more terms they call like fixed die routing. So usually that's the case that we're doing. So by the time we get to this point, our die size already fixed, right? The layer already fixed. So we're not gonna add another layer if we can't route, right? So usually that's the case. Um, but with old technology, they say, well, there's an option with the variable die routing. Um, the resource can be changed, right? They can add a layer, so we have a more routing resource, right? So they start with like 3 layer, and let's see if they can route it with 3 layer. If not, they can just like, okay, let's do 4 layers, right? And yeah, a couple of about the wire pitch and the wire spacing. So I think you have some pictures here. Okay, so these are the some of the terminology that we talk about on a previous slide. So as you can see here, these are what I call a congestion map, right? So it's color coded. So as you see, whenever you see the red, that means it's high congestion, right? So the blue is good, the green is bad, and the red is really, really bad, right? So So that the goal for routing is we don't want to see red, right? We want to see a few green, but not red, right? So mostly blue, a few green, right? So but not red, right? So red is very much trouble, right? Whenever you see red, yeah, we in trouble, right? So the top here is the channel, right? So as I talk about, so in this case, it's the top and the bottom, right? Whereas you have the pin and the signal just connect between them, right? So, and Swiss box is a combination of the two. So instead of just bottom, top and bottom, left and right, now we have just like a square, right? So you can connect, top to bottom, left, right. Um, so yeah, these are just want to make sure. I think it's totally obvious, but I think it's important to make sure we don't get confused, right? So the wire pitch is the distance between essentially the middle of the wire to the neighbor, right? So, and this is the wire spacing, right? So the distance is just the shortest between the two wire, right? So is there any questions so far? Because today I've just go to, I'm not gonna go any,
So we had one question come up in the chat,
okay.
which is, can you talk more about congestion and routing? What does it mean, available tracks resource, and how do we know what it is? And if a required track is higher than the limit we have, how do we fix that?
Okay. Yes, it's a little bit early for today's session because we're gonna go through that during global routing, right? But essentially, I I'm gonna go ahead and then talk briefly about it. So like we mentioned about before, we have the global routing cell or G cell, right? So imagine you divided the die into those square, right? And then global routing, what it does is assign, right? Based on the pin, right? The location of the pin and how how's the pin are located, right? Certainly they has to belong to any given pin has to belong to a Z cell, right? Have to a location. And then based on that, all those location, global route, global routing or global router gonna assign track, right? Routing, for over the net. And then so every G cell gonna have a certain net going through, right? So and the tool keep track of it, right? So they know exactly how many track available per G cell. But then if you need more, right? Because so let's say locally the pin count is just so high on some area. I mean you need more than the available track. Then you have an overflow, right? Let's say you have 10 track available, but you have like no, you have like in order to connect all those pins locally, um, say it need like 11. That means you need one additional track, right? That's the overflow, right? And then if you get to a point, say, wow, I get like 8. That's pretty high. 8 out of 10 is pretty high, right? So there's a metric you can define it, right? What the percentage you consider is a congestion, right? Is that 80%, 90%, or 70%, right? So the within the tool, they they have the mechanism to display those metrics to you in graphically, so you can zoom in and you can see, you know, the number. Let's say, you know, 10/8, right? All those numbers, you can be able to see it. And I think we're gonna have that in the lab as well. So the short answer is yes, we're gonna talk about it. And but for now, yeah, just think of this as when you need more than what you have, then you have congestion, right? I think that's probably the simplest way to look at it, right? So okay. Is that the only question? I hope I'm not going too fast.
Yeah, that's the only question we have so far.
Okay. Okay. So we're gonna talk about what coming in, right? So so for the flow that we're doing, it's very much is, you know, when we're done with CTS, everything is contained in the database, right? So even though we say in here is we we have a netlist, right, and a place design, but these are actually kind of like built into the CTS database, right? But potentially you can have a netlist, and then you can have let's say a def, right? So you can combine those two and as an input to the routing stage, that's fine as well. But in reality, you know, we run through the flow, and prior to this step, we finish the CTS step, right? And this is just a continue of the, you know, just pick up the CTS database. So which has the netlist in it, it has the place design, right? And some of the CTS, I think Bat already talked about it. So it has the non-default route for the CTS, right? So up until this point, the signal is not routed. The clock is routed, but not the signal, right? So, and the clock can be rerouted as well. Uh, and then understanding the design, we, you know, so usually initially we just let the router do its thing, and then it's come back with a it's not so good result, right? It's it put the route where you don't want it to be. Then that's where the routing blockage come in, right? So we look at the congestion, we look at the route, and then we say no, I need to redirect certain route, you know, somewhere else, right? Because more often than not, the tool gonna, whenever it see the resource, it's gonna go, right? So it's all based on a cost function, right? So the distance, you know, it look at many different things. So it's gonna see what are viable to it. So sometimes we have to help the tool say, no, don't do that, right? I need certain area to be up limit to the router, right? Don't go in here, because if you go in here, you're gonna get stuck, right? That's where we go and we add the routing blockages. And obviously, you know, to this point, it's more like technology data, but we don't actually go in and put it, you know, additional technology data here. That's part of the data import, right? So So if we prepare our data correctly, we don't have to do it here. But once in a while, say late in the design, and then we figure that we actually didn't import the design correctly, right? We do miss some information. So additionally, you can add them, right? So those are the input to the route, right? So very much the key is a place a place design, right? Where things are already placed, and now the router job is to go and connect everything together, right? So. Okay, so the next one, we talk about the constraint. So what are to be considered as the routing constraint, right? So certainly the routing layers, right? So we can tell the router how many layers, right? We can add in the routing blockages, right? So if you look at the chip, whenever we have macros, right, the layers over, we can't route through the macro. So usually we can only route over, and sometimes you can't even route over, right? If the memory use up all the layer, all the available layer, then you can't route over. You have to go around it. So that's the constraint to the router, right? So and then once in a while we have a special net, or very sensitive net, right? So probably similar to the clock net, but in this case, it's a signal net that we know that we have to take care, give it special attention. Then we can create, NDRU for it, right? We can route that net on certain layer with a certain width and with, certain spacing to the neighbor, right? Or even we can add the shielding, right, on the sides or top and bottom. So those are the options that we can play with, right? So usually those special case we want to do upfront, right? So a lot of chips that we do have a lot of analogs, right? So the consider like whenever you have the analog portion and the digital portion. So the digital, they usually consider very noisy, right? So and then you have an analog signal that come through or near the digital portion. You have to pay good attention to those signal, right? And usually we don't want to do it here during routing. We do it way before, right? So those special net, we're gonna route them first, right? And we shield them, eventually isolate them, away, you know, from the rest of the signal, essentially the random signal, right? So the one that we say, make sure that yes, whatever that happened out there, I want to shield the signal, right? I don't want noise, and then of course the timing requirement, right? It's if we do a chip and say, well, just route it for me, right? Regardless of the timing, then this is not a real chip, right? So every chip that we do has to have a certain performance, right? So and that on top of whatever you know, all the things that we need to do to make the chip work is have to perform, right? So any questions so far for me?
Students are being awfully quiet tonight. We don't have any questions. And I'm not seeing anything in the reactions. So students, if we're going too fast or too slow, use the reaction button to let us know so that we can adjust appropriately. And ask your questions in the chat.
Yeah, because today I think that's all I prepare for the routing introduction. Let's go back here. So because we do have how many weeks? Yeah, we do have 3 weeks dedicated for routing. So that's why we do have time to go to the global routing and the detailed routing in detail. So today is just the introduction to the routing overall, right? So okay.
And we do have a question
Let's
that's
see
come in.
some chat here. Okay.
Yeah. Can you explain more about shrinking geometries while increasing number of layers?
Okay. So I think that's one of the challenges, I think. Okay. So as you can see here, right? So when I'm talking about technology node, right? So we go from 130 to 90, 65, 45, and 32. That's what I meant by say make it reducing or shrinking, right? So the device gets smaller, right? So that's how we measure, right? So these number indicate the size of the device, right? So that's shrinking, and it make it smaller, right? More challenging to manufacture, right? So that's a challenge in itself. And then so it in this picture it doesn't show you that, but the wire actually gets smaller. This doesn't represent the correct sizing for the wire. It's just relatively within the technology. Then the way you look at it, say just within here, then yeah, we have like extra layer here for let's say the 90, right? If you go from 130 to 90, then we have extra layer, right? That's have the higher, thicker, and the wider metal, right? So, and then 65, we have more, right? So I think 130 is like just like I think they call it X layer, right? And then like we have like XY, and then we have XYZ, right? So yeah, if you look at the number here, it's going from 130 down to 32. That the device getting smaller, right? Shrinking, right? And then you look at the metal stack, right? So we have about 6 layer here, and now we have down to 32. We have about 10, right? So this is 6. yeah, 12, right? So the layer, not just the number of layers increase, but they not uniform anymore, right? So if you look at 130, they all the same, right? Just the X layer, right?
And if I can add to that, so you might wonder why, right? So as you know, when you get to smaller nodes, the RC delays becomes more prominent. So as compared to the device delays, right? Transistor delays, because the transistors shrink faster than the RCs. So now you have more devices, more functionalities in the same area. So without adding the additional wires, first of all, you cannot wire without the DRC within a small area because the transistor shrinks so fast. And two is that because of the RC delays in smaller nodes, this is only 32, but you look at sub 10, right? 5, 3, 2, 1. The wirings, the wire delays become, more and more prominent. It's a lot worse than transistor delays. So you can see the growth in terms of the RC, in terms of the wiring thicknesses. See it from thin to a little bit thicker and thicker and thicker. TSMC called them, thick, ultra thick, etc. So you see the growth on the thickness. So why the thickness? Because when you shrink the RCs, shrink the wires, the Rs, because of the thin wires, the resistance of the wires become more and more. To increase the speed or to meet the speed requirements, you need smaller Rs. So you cannot shrink on the X dimension. So you cannot grow in the X dimension to improve the R. So you grow vertically. So that's why you see these thicker wires, and then many of them added just to be able to route within a small area. Yeah, that's why you say shrinking geometries increase the number of layers and also increase RC delays with respect to transistor delays. Yeah. So, by the way, I delayed this introduction to let you know Tien Pham is a pioneer in IC design in Vietnam. In 2005, when not many companies did the IC design, he worked for a company called Signet Design Solutions, which is the U.S. company. He went to Vietnam and opened up a design center there in Saigon. And he trained quite a few people there in 2005. And later on, they became key members of the IC design team in different companies. Yeah, including Synopsys, Renesas, you name it. There are people from the team that he trained in Vietnam playing key positions in various companies, in one of the 50 companies that do an IC design here. So just to let you know how special Tien is to this training team, and so he's done the training many years ago, like almost 20 years ago, and we're lucky to have him help us over here. So I just want to add that, and thank you, Tien, for a very good lecture today.
Yeah,
So
thank you, Phil, for the introduction. Yeah, I mean, yeah, today I want to keep it simple, just the introduction to the routing. There's a lot of things that we can go just depend on how deep we want to go. But like try to keep in mind of the this is the fundamental, right? So we just want to make sure that we
Hey, can you go back to that slide of geometry shrinking? I have a couple of things to add.
okay.
So you can see the another additional complexity that if you shrink the, in addition to what Phil was talking about, if you shrink the geometry down to lower, to like sub 10.
Nó là gì? Rất là một cái bảng mô tả mà nó tạo ra những cái
Hello? Okay. So
Conversation.
okay. So in addition to the challenges, the DRC is also a huge challenge. So at low geometry, there's the impact, the cross impact or the cross effect, not just from near neighbors on the side to side, but it's all 4-dimensional. Is you got to check DRC from top, bottom to top, side to side. So it's no longer just the 2-dimensional. Now it's a 4-dimensional impact on DRC. So the DRC rules will multiply really fast. Okay, so that's one of the complex down there. And also when the wire is so small that when the manufacturing when they're etching, so they can actually the impact they can edge so that it over edge the wires. So what happened is there's no longer a single pattern. They do what's called double patterning, which is two patterns for one wires so that it can maintain the shapes. Okay.
And Bach, it looks like we've got a question. It's right along this idea of 2 dimensions versus 3 and the shapes of the wires. Wenhan Hai asked, in one layer, can we change the thickness of metal?
No, so the layers you go from metal 1, the layers, the thickness are actually already fixed. Okay, so you look at the 32 nanometers, right? Metal 1, 2, and 3. So 1, 2, and 3, all those number of layers, the thickness are fixed. Okay, you cannot change the thickness of the metal. You can choose a different layer. So for example, if you see the higher layer is slightly thicker, right? So you can choose to route in those layers. So it's thicker, but you can't change the thickness of the metal. You can change the layer routings depending on the thickness that you like, that you want, but you cannot change the width. The thickness of the wire.
Yeah, the reason for that is that's a recipe for manufacturing, so
Right.
you cannot change it. But design-wise, you can change the width, but not the thickness.
Right, you can change the width of the wires.
Yeah.
Provided
Can-
you
Yeah.
DRC rules.
Yeah.
One
Can-
one thing I want to mention that sometimes it's if you think can you change something or not, because you think about the way that the chip is manufactured, right? Everything that we do here has to be modeled in some way, right? So the thickness has to be on a certain layer, has to be it has been modeled, right? So if we change, then this is no longer work, right? So all the RC is all the timing table, all of those extraction, all of those number is no longer valid. So that's so for thickness you can't, right? So just
Yeah.
think of that. It's just like a quick check, right? If you change something and then your model is no longer valid, then yeah, that means you just can't do that.
Yeah, there's no way in the design database you can change the thickness because it came from the model. Yeah, can you go to page 9?
Okay.
Yeah, so I just want to address earlier question from Nguyễn Lê Minh, even though you're gonna talk about it later, but since the question is fresh in the mind, so when Nguyễn Lê Minh asks if the required track is higher than the limit we have, meaning that if you have a G cell, right? If you have a G cell and overflow, this red sometimes it cannot. It depends on your filtering, but say usually So if your tracks allow 10 of them, and by a track assignment you have more than 10, say 12, right? So keep in mind, these are just assignment, right? They, in the actuality, the router will try to follow the requirement by by putting the wires through these G cells, but they don't have to. For example, over here, if you have say a cell here, and you need to talk to a cell here, and it's in critical path, and the cell has to go through this wiring, right? But it can, so the tool will actuality is the tool have to do, go into the blue and zigzag around and go to the target. So and it will do that, but the problem with that is that it will make timing worse, meaning it cannot meet timing if it cannot have a short wire between the two cells. So the congestion to show the ability of the design of the router to be able to route cleanly. So the point being, without the timing, probably it will route cleanly because they are blue around, so it can just go through all the blue, and go through all the blue and then go to this target. Or but if you do this, then the timing become worse. So the router, the algorithm would be I give the priority for timing, meaning when I route, I need to make sure that the timing critical signals are treated well. So it is a combination of timing requirements and the congestion that give your router the problems are not. So the question, the answer is, if the required track is higher, how do we fix that? Like I mentioned, the router can route without DRC, but because of timing, then it cannot. So you fix that by techniques that the Tien will go over later on. But I just want to make sure I address that question a little bit further. That's
Right.
it.
Yeah.
Yeah.
Yeah. Yeah. Thank you, Phil. And another thing is, it's always a trade-off, right? So I did mention about so there's many technique, right? So let's see what slide I'm talking about here. So there's many things we can we do have some time, so maybe we can expand some of these topic here. So previously I was saying, yeah, if we create a really good floor plan, we did an excellent job, during CTS. And you look at the congestion after CTS, you look at the timing after CTS, it's perfect. It's met timing, right? Skew is excellent. Everything is right. And then you go to, routing. And then you do global route, still good. Congestion is good. Any matrix that you look at is perfect. And then you do detail route. And then you have timing violation. So the question to you is, where's that violation come from then? Right? We did an excellent job in previous state, right? Good floor plan, great CTS. Even global time routing is excellent. But then when it's actually put down the real wire, right? We do have timing violation, right? So
Tien, we're a little bit after the hour. If you'd like to take a 5-minute break at this point.
yes, I think probably yes, we can do 5 minutes and then kind of like think of that, and then I think there's quite a few things that I want to expand a little bit more because we do have time. So thank you, Dave.
All right. We'll come back at 12 minutes past. I'll have a clock on the screen for us.
All right, thank you.
All right, Tien, it's a 5-minute break if you're ready.
All right, thanks there. So let me share my screen again.
There's a question in the chat, Tien.
Okay. Let me Okay, so look at it. Let's see. Okay. Is it because in routing, all the data path will have real RC? Real
There's
route.
one before that.
Okay, that's okay. In global route step, using DCell can predict routing congestion. But how can it calculate Y length when it's not actual route? Okay, so for that one, so I mean, the tool is getting very, very good now, right? So without, yes, it is it's calculate planning, right? So essentially it say I will put down a wire here. So it does plan to put down the wire. So it does know in the timing calculation, it use that planning, right? So it does know the wire. It's not a real wire, but it has everything, all the intention of that wire gonna be, right? So it's have to assume that's the detail route we'll use that planning, right? I'm gonna put a manual 2 here, go using this track, exactly what layer it is and what track it is. So it use that information. So it does know the Y length, the layer and everything. And then it can calculate precisely what the delay or the RC for that, even though it's an estimate. But it's very, it can be very, very precise actually. So the answer to you is yes, it is a prediction, but it can be very accurate. So I think Gokukai essentially trying to answer that question is that because routing for the data path will have real RC, real route, so that the net could be detour, right? Right. So I think, right, so I think there's a couple component to this, right? So, and I think is that Nguyễn Văn Duyên, right? I think he's right in a way that he's suggesting the there's gonna be a disparity between an estimate, or a prediction and the real route, right? So the global router gonna plan out everything, but when the detailed router come, not all of those planning will be used, right? Maybe it's like if there's no congestion, more likely a high percentage of the global route will turn into real route, right? It's just a small percentage of those global route will be not, right? Because it's locally, that's something because of DSC that the detail router had to reroute, but because there's no congestion, right? So more likely that's the high percentage of that global route will turn into real route. So, and then the Google Thai suggesting that the difference is between real RC Yeah, but I was talking about the incoming data is so good. Essentially, we have no congestion, right? that means more likely we're not gonna have the detour, right? So usually, personally, I've seen this before, and usually because we don't have the correct, let's see here. So usually it's happening into, right, so two things, right? So it could be due to the incorrect, it's the disparity between the prediction and the real route, right? But because the assumption that I make earlier is that the congestion is so good, so more likely that that's not the cause, right? The whatever that we plan will turn into real route, right? Because there's no reason to reroute something if there's no congestion, right? So I'm gonna be just like a tiny fraction of the route has had to be rerouted in certain way due to DSC, but and then another thing is global Thai real see. I think here gets a good point here is that the signal, the SI, right? So usually by default, when we run global route, we do not consider the SI, right? Because it's just a matter of trade-off, right? So when you do the global route, by nature, it's not a final route, right? So unless you know ahead of time that your design will have some SI issue, right? So by default, global route are not going to consider timing ribbon or SI, right? So you can turn it on, but it's going to take longer, right? So by default, the tool it's a trade-off between quality and runtime. So by default, you know, the tool not going to run with timing ribbon global route and crosstalk aware global route, right? So, and once in a while, that happen to be, you know, the key difference between the global route and the detail route, right? So locally, there's some crosstalk, right? So you have a long wire running in parallel, you know, and then it's just bad. There's no congestion, right? But the tool didn't look at the crosstalk. So all these, you know, long wires just running along, right? So if you don't look at the crosstalk, they are fine, right? They're perfectly fine. But when you look at a crosstalk, they problematic. So, and I think Phil wanna add something.
Yeah, I certainly can. So I want to go way back, right? So if you think about timing results, when do you start looking at timing closure? Can somebody tell me during the RTL to GDS, when do you start, you know, timing analysis? Type in the chat, which step do you start timing analysis? The earliest step that you look at. So I'm going to interaction here because we do have time, Tian, if you don't mind.
Oh,
So
sure, yes.
right. So please type in the chat. It's just has for your understanding up until now. When do you start doing timing analysis? Meaning that you analyze, does your design meet timing constraints in terms of frequency, right? Please type in. Try your best, and no answer is stupid answer. So just type it in. I just want to make sure, yeah, we can cover things that are not clear to you. Trương Tuấn Vũ in logic synthesis and in PD. Anybody else? Which part you mean of PD steps? You right. So what are the PD steps, right? Synthesis, place and route. During place and route, you have import, floor planning, placement, CTS, routing optimization, post CTS optimization, all the steps that you listed here on the top page here, right? It's floor planning when you start looking at timing. Should check from floor planning, right? Okay. All right, so in general, the answer is right. Very early on, but in this case, the most correct answer based on the question would be Trương Tuấn Vũ in logic synthesis. So when you synthesize, you already say, does your design meet timing? So what do you think the synthesis tool estimate or calculate the RCs? What do they do to calculate the RCs? And so it's just, so when you look at timing, right, you're using Weiler model, Trương Vũ said, yeah, when you look at timing, everything, so the synthesis, place and route, meaning floor planning, placement, CTS, routing, everything will have the same timing models. What are those? What are those? Those are the .lib, right?